A lot of MCP content stops at serving tools, but real apps need robust clients too. I'll build a Python MCP client with Auth, timeouts, and retries, so remote tools don't become a reliability hole. This is the workflow you'll know how to run when we're done, which authenticates to a remote tool, enforces a time limit, and retries safely. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Many teams treat the MCP server as the hard part and hand off a raw client to the app. That is where things break. Servers may restart. Networks can be slow. Auth can expire. Success looks like predictable calls that either finish quickly or fail in a controlled way, so your app can recover or retry safely. For a data scientist, that means fewer silent failures during batch runs and fewer mystery timeouts in pipelines. At a high level, an MCP client is the glue between your code and remote tools. You want it to do 5 things well. It should connect reliably. It should prove who you are. It should enforce a time budget. It should retry intelligently. And it should keep calls idempotent when needed. Those features let you call remote services like local functions, but with production guardrails. The idea is simple. We will build a client that starts a session, checks which tools are available, authenticates with a bearer token, measures latencies to choose the faster route when there are options, applies bounded retries with exponential backoff, and finally runs a guarded sum operation that includes an idempotency key. Strengths are clearer error behavior and fewer hidden retries. The trade-off is slightly more client code and a couple of parameters to tune. We will build a small local example so you can see each behavior. The code will be readable and focused on behavior, not on exotic libraries. You will see how timeout values and retry limits change outcomes in predictable ways. Now, let us begin by starting a session and confirming the server shows its tools. Now, we will create a client and list tools. This snippet creates a simple MCP client, connects to a local server, and lists available tools within a timeout. The variable CMD defines a Stdio-launched server process, so mcp.Client.Stdio can establish a session. The object client is the long-lived handle that will be reused across steps. The call client.listTools requests the registry of remote tools, and the variable tools holds the returned list of tool descriptors. The expression tool count computes a stable count by sorting names before measuring length, which prevents flaky ordering. Increasing timeout on mcp.Client.Stdio can mask slow startups. Decreasing it fails fast. The printed connected tools confirms a working connection and visible tool inventory. Next, we will attach authentication and verify who we are. This example applies bearer authentication to the MCP client and verifies it by calling a whoami tool. The variable token reads MCP token from the environment, and client.setAuth attaches it, so subsequent requests include the authorization header. The function client.callTool issues a whoami method with no payload to fetch the authenticated user identity. The dictionary res is the JSON result, and user extracts the username, falling back to anonymous if the server omits it. Raising the timeout to 2.0 seconds tolerates slower auth checks. Lowering it fails quicker during incidents. The printed auth user shows the identity recognized by the server, proving auth works. Next, we will measure 2 ping routes and pick the faster one. This snippet compares 2 MCP ping tool calls and selects the faster one by measured latency. The function client.call tool sends ping with distinct IDs using a 0.3 second timeout and a single retry to bound tail delays. The variables A and B hold response objects expected to include a latency-ms field produced by the server. The tuples PA and PB pair the numeric latency with the associated ID for a clean min comparison. The best tuple is selected by latency, yielding the winner and its timing. Shortening the timeout tightens SLOs but increases misses. Lengthening it improves success at the cost of latency. The printed faster ID and faster MS highlight the quicker route. Next, we will configure retries for an unstable endpoint. This snippet configures bounded retries on the MCP client and invokes an unstable remote fetch to observe attempts used. The call client.setRetry sets exponential backoff with a base backoff and small jitter to reduce synchronized retries, and max limits total attempts. The function client.call tool triggers unstable fetch with a 1-second timeout and explicit retries, so failures are retried within guardrails. The variable res holds the server's reported attempts, and at reads that count to show whether a retry occurred. Increasing max improves success rates under transient faults, but raises latency. Increasing backoff reduces load, but slows recovery. The printed retry attempts used reports how many tries were needed to succeed. Next, we will run a production-safe sum with idempotency and Auth. This example performs a production-safe sum using the MCP client with idempotency, Auth, timeout, and a retry. The variable REQ holds two addends and an idempotency key so the server can deduplicate repeated attempts. The call client.call tool executes sum with a 0.5 second timeout, a single retry, and require auth to enforce that authorization is present from earlier setup. The dictionary res is parsed for value and latency ms, providing a computed result and timing. Decreasing the timeout sharpens SLAs, but risks cancellations. Increasing retries can salvage transient blips, but may raise costs. The printed, safe sum, and duration ms confirm a correct result delivered under guardrails. This toy example maps cleanly to real work. Replace the local server with a remote service. Use the same token flow. Keep the idempotency key when the operation is non-trivial. The client patterns remain identical and prevent subtle duplication or mystery failures. Recap. What it is: a small MCP client that connects, authenticates, times out, and retries. When to use it: any pipeline calling remote tools where reliability and predictable failure are important. One caveat: client-side retries and long timeouts can hide server slowness, so tune limits carefully. Next step: scale this exact approach by collecting latency histograms and increasing the maximum retry only after you analyze where failures happen. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.